Okay, so I'm going to now introduce some kind of LP type proof system. It won't be quite the same as this LP proof system I've talked about before. And I'm going to introduce it through an example instance, namely an example instance of the max 2-sat problem. Okay, so consider this particular instance of 2-sat or max 2-sat. I have 4 variables here called A, B, C, and D, and I have 5 clauses. 3 of them have length 2, and 2 of them have length 1. And it's a maximization version of this problem. So I want to make truth values for A, B, C, and D such that as many of these clauses are satisfied as possible. And I hope you can easily check that the optimum here is 4. It's impossible to satisfy all 4 clauses. Perhaps you can think about why. One reason is you can view these clauses in the middle as like implications, if you remember your basic logic, and this one is the same as like A implies B, this is the same as B implies C, and C implies D. So it's impossible to have all 5 clauses satisfied, because if A is true, and A implies B is true, and B implies C, and C implies D are all true, then D would also have to be true, but this clause is asking for D to be false. Yeah, we had a question in the chat, is max 2-sat NP hard? And we had an answer in the chat, yes it is NP hard. So deciding if a 2-sat instance is 100% satisfiable is solvable in polynomial time. But if you solve it and find out, no, it's not 100% satisfiable, and you'd like to know, well, what is the largest fraction of clauses I can satisfy, or the largest number of clauses I can simultaneously satisfy, that harder task is NP hard. Okay, great. So we might try to use like a proof system to establish an upper bound on the number of simultaneously satisfiable clauses. Okay, if we were not like smart enough as humans to just see that the answer is 4. So we're going to again have 4 indeterminates here, standing for the truth assignments, 0, 1 truth assignments to the 4 variables. And we're going to have axioms. We'll always have these axioms that they're between 0 and 1. Although we won't actually need those, I don't think. And notice there's no additional axioms here. Unlike in the independent set problem, there are no additional axioms about how the x's are allowed to be, that we're imposing on how the x's are allowed to be satisfied. But our objective is more complicated here. So let me just explain the objective function I wrote down here. I wrote down some linear expression, although it's not, well, sorry, it's not linear. I wrote down some expression. It's not linear, though. It looks like a polynomial of degree 2, because it has these terms. And what I've done here is sometimes called arithmetizing a SAT instance. So you see this part of the polynomial corresponds to this constraint. It's just xa. It's 1 if a is true and 0 if a is false. So that represents the indicator that this constraint is satisfied. The more complicated thing is here. So let's look at this expression, 1 minus xa plus xa times xb. So I just wrote this down as like a little polynomial which captures with a value of 0 or 1 whether this constraint is satisfied or not. Okay, so imagine, let's say that A and B are both false. That satisfies the constraint. And indeed, if you plug in xa and xb to be 0 here, you get 1 minus 0 plus 0, which is 1. Or if A and B are both true, so they're both 1, the constraint is again satisfied, and you here get like 1 minus 1 plus 1 times 1 is 1, so you get 1. So again, it's correctly computing that this constraint is satisfied. And the point is that, like in the unsatisfying case, if A is true, or 1, and B is false, or 0, the constraint is not satisfied. And indeed, here you get 1 minus 1 plus 1 times 0, which is 0. Okay, so this little expression, the whole point of it, this degree 2 expression, is that it captures whether or not this clause is satisfied. Okay, and so we've written down this expression for all the clauses. Here I wrote down 1 minus xd to capture that d is supposed to be false. Okay, and so this, if I didn't have this this relaxation, or if I didn't imagine that or rather, if I really insisted that the xi's were always 0 or 1, then this would sort of exactly capture this max 2-sat instance. Okay, so it's a bit different though, because we have inequalities here involving a degree 2 polynomial, but let's just run with it for now. So in this new proof system, this new LP type proof system I'm inventing, now my lines, I'm going to allow degree 2 inequalities. Okay, my axioms happen to be degree 1, but I'm going to allow degree 2 inequalities. And well, let me talk about this a bit more. So actually, if you just expand this out, and rearrange it a little bit, you get that it's exactly equal to 4 minus this expression I put in parentheses. And now I'd like you to observe something here. So take a look at this expression, xb minus xa times xb. I claim that for 0, 1 values, this expression is always non-negative. No matter how you set these two variables to 0, 1 values, there's 4 possibilities. One way to see it is if you just factorize this a little bit, it becomes 1 minus xa times xb. You see that like xb's value is either 0 or 1. In particular, that's non-negative. And 1 minus xa's value is either 0 or 1. That's also non-negative, so the product is non-negative. Okay, so it's like a little fact of life that if these x's are supposed to stand for 0, 1 variables, then this expression here is non-negative. We have the same expression here, the same expression here. So you see, if our proof system could somehow just realize this like simple fact that, you know, whenever you have something that looks like xb minus xa times xb, it's non-negative, then it would, you know, sort of quote unquote realize that this whole thing in the parentheses was non-negative. And therefore, the objective function is 4 minus something that's non-negative, which, you know, implies that the objective function is at most 4, which is great because that's what we're trying to do. We're trying to bound this objective function, upper bounded, and 4 is actually the correct optimal bound. So what are we going to do? Let's just add this being non-negative as an axiom to our proof system. Sort of a bold move. And what I'm going to do here is sort of develop in like sort of an ad hoc way, like a new, more powerful proof system, and I'll try to motivate it as I'm going along. And then at some point I'll pause and define it properly. But here I'm going to sort of imagine sort of heuristically start building up a new, more powerful proof system. Okay, so this was sort of the proof system we started with. You have a bunch of indeterminates. Maybe these are the axioms so far. The lines we're going to allow are degree 2 inequalities. And let's make allow some new additional axioms that you're always given, regardless of the instance, that look like this. You know, 1 minus xa times xb is at least 0. Well, let's make this a bit more general. Let's say that, you know, you have n axioms, and we're going to have an axiom that looks like this for all pairs I and j. And, you know, it's also logical to add the axioms that look like this, just again, on the theory that if xi and xj are supposed to be 0 and 1, then, you know, this should be non-negative. And also let's add this one. So if xi and xj are supposed to be 0 and 1, then 1 minus xi and 1 minus xj are also supposed to be 0 and 1. So their product is non-negative. So these are all like, you know, sound axioms to add. Sound here meaning that they're true, assuming you're trying to capture the fact that xi is supposed to stand for a 0, 1 value. And, you know, if you have n variables, this is like on the order of n squared extra axioms. So that's, you know, n squared is a polynomial, so maybe it feels fine to add these in. And now we're going to keep the same deduction rule that you can take non-negative linear combinations of axioms, but now you potentially have more power because you can, you know, I don't know, take all these axioms and combine them in some cool ways, hopefully, but taking nonlinear combinations. And actually, I'm not going to prove this, but it's a non-trivial theorem that this proof system I've sort of just explained to you is complete for the problem of two-sat satisfiability. Okay, and what I mean by that is precisely the following. If I give you any two-sat instance, which is, let's say, has m clauses and is unsatisfiable, you can always derive from these axioms by taking non-negative linear combinations. You can always derive opt is at most m minus 1. Okay, where opt here represents like the sort of arithmetization of the two-sat instance. Okay, so this sort of new proof system with degree 2 inequalities is really good if your whole goal in life is to, you know, detect satisfiability of two-sat instances. Okay, any questions? Okay, so let me consider similarly such proof systems for max-cut, sort of our favorite basic CSP. So here's our favorite simple instance. It's a 3-vertex graph triangle. And as we know, the maximum cut here is of size 2. There's no partition that cuts all 3 edges. So here again, we can imagine, this proof system where, x1, in contrast to the previous lectures, let's go back to the x's standing for 0 or 1. It's a bit more annoying here, but I wanted to stay consistent that the x's stand for 0 and 1. So again, we'll have a variable for each vertex, 0 or 1, that represents whether it's sort of in the cut or outside the cut. And now arithmetizing whether you cut an edge is a bit annoying. So like this edge here between A and B, I claim that this expression captures in a 0-1 fashion whether the cut defined by xa and xb cuts this edge. Okay, so you see if they're both 1, you get 1 plus 1 minus 2 times 1, which is 0, not cut. If they're both 0, you get 0 plus 0 minus 2 times 0, which is 0, not cut. But if 1 is 1 and 1 is 0, you get 1 plus 0 minus 2 times 1 times 0, so you just subtract 0, so you get 1. Okay, so this little degree 2 expression encapsulates whether or not this edge is cut. Okay, and I've written the analogous expression for the other two edges here. So we have an objective we're trying to upper bound, which is like a degree 2 polynomial in the variables. I just sort of rewrote it a bit here. And our dream is to somehow, establish the dream that it's at most 2. And in this LP type proof system I've been talking about, I mean, we have all those axioms that say, like xa, xb is at least 0, and xa times 1 minus xb is at least 0, and so forth. You might hope by taking a suitable non-negative linear combination of those, you could derive, the inequality that looks like this expression is at most 2. Well, it's not very easy to see this, but I'm here to tell you it is a fact that you cannot do that. There's no, it doesn't work. The best upper bound you can get is not 2. And in fact, there's no way to deduce from those axioms that this max cut is at most 2. So we could, just grin and bear it and say like, well, I guess this proof system is not so good about knowing the max cut in a triangle graph. But we could also try to, go on and say like, well, maybe we can put in some more axioms that are true of 0-1 variables, and that'll make the proof system more powerful, better at proving upper bounds. Now, one thing you could do is sort of almost like cheating. You could say like, well, it's a true fact that we all know that this expression here is at most 2. Because, we can look at this triangle graph and be like, I assure you the max cut is at most 2. And this is like an inequality involving the variables. It's like the fact that this is at most 2 doesn't even really have to do with max cut. It's just a true fact that this expression is at most 2 for all choices of 0 and 1 for xa, xb, and xc. So we could be like, hey, let's just make that an inequality, an axiom. Feels a little bit like cheating because, it's done to exactly solve this. Although, let me actually say, we're going to do something kind of different, but let me actually say it's not so much cheating. It's not a totally illogical thing to add. And it's not like its only purpose in life is to, get this triangle exactly solved. So here's an exercise for you. If you throw in this axiom for all triples of variables, indeterminates, then for any cycle graph on n vertices where n is odd, the true max cut is at most n minus 1 because odd cycles are not bipartite. And actually, you can derive this fact in our little degree 2 inequality proof system using only the original axioms plus this new axiom about triples of variables. Okay, so that's a little bit of sense in which it's not totally just like begging the question. But we're going to go in a slightly more principled direction than this. Okay, so here's the bold new axiom idea. We're going to keep the same inference rules and the indeterminants that are supposed to stand for 0 and 1, but what we're going to do is add more axioms in some sense. So what we're going to do is pick a parameter k, and then I'm going to allow you as an axiom any true inequality that involves at most k variables. Think of k as like a constant like 2 or 3 or 5. And what does true mean? True means it's like a true inequality about 0, 1 valued variables. Okay, so you might be concerned like, wait a minute, there's like infinitely many true inequalities about, 3 0, 1 valued variables. So it feels a little weird to say like, oh, I'm going to add all of them. In a certain sense, though, I'm going to claim on this slide that you actually only need finitely many of them. So why do I say that? Well, let's say k is 3, and suppose you wanted to use this axiom. Let's say p is a polynomial involving the variables x1, x2, x3, and suppose it's a fact that this polynomial is non-negative whenever you assign, do one of the 8 truth assignments to x1, x2, x3 with 0 and 1. And so, up here I'm saying like, oh, that's true. You can take that as an axiom. Think for a moment p of p not as a formal polynomial, but think of it as really a function that maps 3, 0, 1 bits to a non-negative number. It must do this because I'm imagining that it's truly non-negative for all these 8 choices. And it's a fact that any such function is uniquely expressible as a multilinear polynomial. In fact, the proof of this is the exact same fact as the sort of interpolation proof we did for Fourier expansions. In the Fourier analysis of Boolean functions lecture, one of the key theorems is exactly this fact, except that we use the notation plus or minus 1 instead of 0, 1 for our variables. And this greater than or equal to 0 is not necessary. Every function mapping n-bit plus or minus 1 strings to real numbers was uniquely expressible as a multilinear polynomial. It's same is true for 0, 1 bits. You can just do a linear shift to change plus or minus 1 into 0, 1. But it's also, clear if you just look at it like this. What I can do is write down these 8 sort of degree 3 polynomial expressions, and I can multiply like this one by the polynomial's value at 1, 1, 1. You see, this polynomial expression is 1 if the bits are all 1, and all these other ones are going to be 0. So I multiply it by the value of p at 1, 1, 1, and I can do a similar thing for all 8 truth assignments. And since we're assuming this polynomial is non-negative on all 8 truth assignments, these coefficients here are actually non-negative. Okay? And now remember, in this proof system we were imagining, I was giving you as axioms that each of these yellow things is non-negative. This expression greater than or equal to 0 is an axiom. And this next expression greater than or equal to 0 is an axiom. And our derivation rules allow you to add up axioms with non-negative coefficients. Okay, and so you can derive this polynomial as greater than or equal to 0, presuming it's true from the axioms. So somehow what I'm saying is like these 8 axioms are sort of like a basis for all true inequalities about 0, 1 variables, about these 3, 0, 1 variables. Does that make sense? Okay, so now I'm going to get more precise about things and make a proper definition. So I'm going to define for you a proof system. Well, I'm not going to define what a proof system means, but you'll get the gist. And this particular proof system, for historical reasons, is called the degree K01 Sherali Adams proof system, sort of due to 2 people called Sherali and Adams. And there's 1 for each value k, actually. You think of k as a parameter, you get different proof systems. And okay, how does this proof system work? Well, you always have like n indeterminates as an ingredient in your proof system, and they're supposed to stand for 0, 1 variables. And your proof lines are going to be degree k polynomial inequalities, given your parameter k. And maybe they should be multilinear, maybe meaning you don't have squares or cubes or anything, just monomials without squares and cubes and so forth. And your derivation rule is going to be the derivation rule we've always used, that you can take non-negative linear combinations of previous inequalities and deduce those as new inequalities. And the axioms are going to be all true inequalities that involve at most k out of n indeterminates. Okay, in the sense that we talked about in the previous slide, if you will. As we saw before, that's infinitely many inequalities that you can take as axioms, but there's sort of like this basis of them, that finite basis which sufficed. And for all, you have sort of one of these basis things for all. First of all, you do n choose k of the indeterminates. And then like for each one, you can either have the variable or 1 minus the variable in this product. So it's like another 2 to the k possibilities. Okay, so like in sort of the real finite version, like all of these n choose k times 2 to the k inequalities are your indeterminate, are your axioms, that they're non-negative. But it's equivalent to like allowing any true axiom about any true inequality statement about k01 variables. And that's the proof system. And you can take it and start to go to town deriving facts that hopefully are useful for combinatorial optimization problems. And I should mention that like you can also like in 2SAT, we didn't have any additional axioms based on the instance, but like sometimes you do. So like in the independent set problem, given a graph, we added like additional axioms that specify that each edge should not have both of its endpoints selected. Those are those like xa plus xb as at most 1 axioms. Okay, so you're allowed to do this. You're sort of allowed, in the proof system to add additional axioms if you want, and then you're trying to derive, true consequences of all your axioms. And notice that, you should try to think of k as like an absolute constant, like 2 or 3 or 5 or 10. And then, n choose k is something like n to the k times 2 to the k. So this whole expression it's good to know that this is polynomial in n if k is constant. Okay, so at least, the number of axioms you have is like polynomial in, the relevant parameter n. And for abbreviation, we're going to call this the SA parentheses K, Sherali Adams K proof system. Okay, so, we can have lots of lectures on this particular proof system. But let me just tell you some properties of this proof system, and they're kind of like proof theory properties of it. So just for a little bit of fun, I'm going to use some proof theory terminology. So first of all, it's a sound proof system. You would never want to have an unsound proof system, but what does sound mean? It means that everything you derive is true. So like when you're imagining a world where all the variables are supposed to be 0 or 1, our axioms are set up to be true, and our derivation rule, which takes non-negative linear combinations of true inequalities, like preserves truth. So that's good. So anything we derive is true. And then you might ask, well, what about the opposite, which is called completeness? Is it true that like everything that's true you can derive? Well, as I mentioned before, in the context of like max cut, at least when k was 2, that's not the case. So actually, this is an incomplete proof system, which means that there, in general, are true inequalities about 0, 1 variables that you just cannot get no matter how much you try to combine the axioms. At least this is true if k is smaller than n. In fact, you can think about this, and we'll maybe implicitly prove it later. If k equals n, so you're allowed to have lines that involve all of the, degree n polynomials, and your axioms can involve all of the variables. Well, actually, in that case, it's obvious. If k equals n, and your axioms allow you to, make any true statement about all n variables, then you can just, anything that is true, you can just derive as an axiom. But in general, even if k is n minus 1, there'll be some things that you cannot derive, even though they're true. Another property of this proof system is that it's called static. I won't get into this very much, but static basically means that the derivations are, without loss of generality, 1 line long. So this is a little bit weird. It's more natural to have like what's called a dynamic proof system, where you make your derivations gradually. You derive some lines, you derive some more lines, you derive some more lines, and finally you derive your conclusion. And in this Sherali Adams proof system, you don't really need that, because like the only derivation rule is taking non-negative linear combinations of previous lines. And so everything is a non-negative combination of the axioms ultimately. So any conclusion you can derive, you can actually derive in like one shot, which is a little bit weird, but we're going to stick with it. I mean, we're going to still think about it as a proof system, even though it has a slightly odd property. By way of contrast, that cutting planes proof system I mentioned before, that was like similar to this, except you could also do this like round down the right-hand side to an integer if all the left-hand side coefficients were integer. That's definitely a dynamic proof system, in the sense that like in order to get real mojo out of this, you have to do like an interlaced combination of like You know, take some non-negative linear combinations to get a new inequality, do a round down, take some more linear combinations, do a round down, take some more linear combinations, do a round down. Like, you can't do the whole proof in one shot. Okay, and one more property of the Sherali Adams proof system, which is sort of the main important property about it, the reason I'm talking about it, is it has this property called automatizable. It's a very hard word to say. You can practice it in your spare time. Automatizable. Automatizable? Yeah, same thing. Automatizable. And what does that mean? It's a property that not a lot of proof systems have, but this proof system does have it, which makes it great. And that means, basically, if a proof exists, you can efficiently find it. Okay, so the property of Sherali Adams proof system is that, like, for any line which is derivable, you can efficiently, an algorithm can efficiently find a derivation from the axioms. Okay, so like for any, in particular for optimization problems, like whenever a statement like, oh, the objective polynomial is at most 7 can be derived at all, then there's an efficient algorithm that finds it. And here efficient means it's a function of the number of axioms. So polynomial in this number of axioms, or n to the order k. I'll explain why in a second, why it has this automatizable property. So it's efficient, you know, if k is any constant, you know, it's efficient in theory land, it's a polynomial time algorithm. And it's still interesting if k is like, you know, log n, you get like a quasi-polynomial time algorithm. Oh, I should mention that this proof system gets sort of stronger and stronger the bigger k is. It makes sense because you're getting axioms about more and more collections of variables simultaneously. And that's why it's called the proof system hierarchy, the Sherali Adams hierarchy, because Sherali Adams 1 is weaker than Sherali Adams 2, and that's weaker than Sherali Adams 3, and so forth and so on. So you get this hierarchy of more and more powerful proof systems, and you can find derivations in them efficiently, provided they exist, in time that's like n to the order k. So it's kind of nice. You have this like tunable power parameter k, so it takes more time to work with these things, but you get more and more power. So let's understand briefly, why is this Sherali Adams k proof system automatizable? Well, PowerPoint's having a little hiccup here. So any, let's say a Sherali Adams k equals 3 proof looks like the following. Okay, so like, you know, because it's got this static property, like the proof, even though you might imagine it like going, you know, in several steps, you can do it in a one-shot way, where you take a linear combination, a non-negative linear combination of all the axioms, like, you know, like all the axioms. You know, these are k equals 3, so you like look at all n choose 3 times 2 to the 3 many axioms. Maybe you're like minimum or maximum independent set, so you have some additional instance axioms. Anyway, like a proof will look like a non-negative linear combination of all these things that adds up to an inequality that looks like beta minus the objective polynomial is at least 0. You know, aka the objective polynomial is at most beta. And so now if you imagine for yourself, like searching for a good proof that looks like this, it amounts to searching for these lambdas in such a way that when you do this add up, you get beta, which is small as possible. So what's nice is, you know, this is like the LP dual. This is like a linear program because you're, you know, beta is a variable and these lambdas are a variable. And you're looking for non-negative lambdas. It's a linear constraint. And to say that this big giant sum holds, it's sort of to say that it holds on a coefficient by coefficient basis. So like for every coefficient, or sorry, I should say on a monomial by monomial basis. So for every monomial, like x1, x2, x3, you see you get a contribution of like lambda 1 here. You get a contribution of minus lambda 2 here. And like you'll get some contributions from some of the lambdas, and like those appropriate sum of the lambdas should equal the coefficient on x1, x2, x3 in the objective polynomial. Okay, so you get like a bunch of equalities involving the lambdas. And so yeah, that's why searching for, and the number of lambdas is like 1 per axiom, so it's like n to the order k. And so searching for the best proof can be done with an LP in n to the order k time. So that's cool. We have these more and more powerful proof systems and an automation algorithm for finding proofs in them. So what is this good for? I mean, is this actually help us solve like new complex combinatorial optimization instances that we couldn't solve before. I don't know, taking k larger and larger. So let me give you a few examples to show that the answer can be yes. So this first example is really nice, and it's going to connect to something we're going to talk about in the next lecture. So let's say you have some instance I of a constraint satisfaction problem, any constraint satisfaction problem. There's a notion given any CSP of what's called a primal graph for the instance. And the primal graph is just an ordinary graph where you have the vertex set is identified with the n variables of the graph. And you put an edge between two variables or vertices if these two variables or vertices are in some constraint together. Okay, so like if it's like a max 3-side instance, you have like a variable for each, you have a vertex for each variable, and you have like a triangle for each constraint plunked in. Or if it's like a 3-coloring instance, like the primal graph is the same as the actual graph. So it's a theorem proved by Wainwright and Jordan, I think were the first to prove it, that, well, let me read it here. If the primal graph of your instance, G, has tree width at most t, I'll say what that is in a moment, then the Sherali Adams proof system with k being t plus 1 it's sort of complete for the satisfiability question. It can derive that the instance is unsatisfiable provided this is true. Okay, so this is a proof system, it's sound, so whenever the proof system can derive like the arithmetization of the expression I is unsatisfiable, that's true. And conversely, if it is unsatisfiable, it has this sort of amount of completeness that if it is unsatisfiable and the graph has this tree width property, t, then this proof system with k being t plus 1 can certify this unsatisfiability. Okay, and so you get a satisfiability checking algorithm that runs the time n to the order t for any instance whose primal graph has tree width at most t. Now, what is tree width? Well, I'm exactly going to talk about that in the next lecture. It's some parameter of graphs that measures sort of how similar they are to trees. The lower the t, the more similar they are to trees. In fact, the graph has tree width 1 if and only if it's a forest, a collection of trees, and has tree width 2 basically if and only if it's a series parallel graph, which I'll say what it is next time. But it's some sort of measure of simplicity of the graph. Okay, so it says if you have like kind of a simple enough constraint structure on your instance, then the Sherali Adams proof system will be good at deciding if it's satisfiable or not. Okay, so that's one example of how you can use Sherali Adams proof system. Here's another one that I believe will appear on your last homework. Consider the max k-sat problem, definitely NP hard, max k-sat. Okay, so just to arithmetize the objective function, which involves clauses on k variables, you need to have lines that are degree k inequalities. So the first thing you could imagine looking at is the Sherali Adams proof system with parameter k for max k-sat. And it's actually not too bad. You can prove it has the following guarantee, no matter what k is. Whenever the true optimum value, the maximum number or fraction of satisfiable constraints is beta, is 3/4 beta, the Sherali Adams proof system will certify that it's at most beta. Okay, so the best upper bound the Sherali Adams can certify will be no more than 4/3 times the true upper bound. So that's pretty all right. Let me give you one more known fact about it to illustrate why you might care. So recall one thing we talked about in the LP lecture was that for the max cut problem, the basic LP relaxation that you would write down really stinks. It's not very good at capturing max cut. And for example, here's a true fact about the extent to which it stinks. If you take a random graph with n vertices and like n to the 1.01 edges, so it's not very dense, average degree n to the 0.01, then first of all, the maximum cut in this graph will be very close to half. The maximum cut will cut barely more than half of the edges, like half plus a little of 1. But if you write down like the natural LP relaxation and solve it, it will only certify that the maximum cut is at most 1 minus a little of 1. Like it'll notice that it's not literally bipartite, but it'll be like, could be very close to bipartite, even though it's like its optimum is as close to minimal as possible. So that's the suckiness of LPs for max cut. And I should say that the natural linear programming relaxation you will write down for max cut is exactly the degree 2 Sherali Adams linear program. Okay, so here I'm talking about the failure of the sort of k equals 2 Sherali Adams to do well at max cut. But here's a theorem that was proved with Schramm in 2019, just last year. If you choose k to be a very big constant, then the degree k Sherali Adams proof system for these random graphs does do a pretty reasonable job of noticing that their maximum cut is barely more than a half. So for a fixed constant above a half, like 0.5001, there exists some constant k such that this k Sherali Adams proof system it basically, can show that the optimum is at most 0.5001. Now, this is not all peaches and cream because, I mean, if you dig into the proof, this constant k is like very bad. Maybe it's 10 to the 100, so maybe you have an n to the 10 to the 100 time algorithm for solving it, which is theoretically polynomial time. Not so great. And actually, another reason this is not so good, you have this extremely slow, quote-unquote, polynomial time algorithm, is that there's a very, by now, maybe to use simple polynomial time algorithm, semi-definite programming that does the job, and even does it a little bit better. So it's a theorem of Zwick that actually whenever you have a graph whose max cut optimum is like barely more than a half, the SDP optimum will also be just a little bit above a half. Okay, even with like this little o of 1 with respect to n going to infinity. So yeah, so this is one reason why, okay, there's some things in life that are better than the Sherali Adams proof system.